I've mentioned the key to solve the problem of dealing with higher voltage, higher reverse voltage, is to use intrinsic semiconductor material. So you can see in power diode, it is not just two layers. In information electronic diode, there's two layers, P layer and N layer. Now we have three layers, P, this is the intrinsic layer, and N. This intrinsic, we take the initial character, therefore we call this structure as P intrinsic N, PIN diode. Okay, so this is why it's called PIN. And because of this intrinsic layer, this diode has the ability to handle very high voltage. And usually this intrinsic sometimes is also, you also put some impurities. It's not pure intrinsic. Here in this picture we put some column 5 impurity. Therefore, it is closer to N material. But the density of impurity is very small. That's why we put a minus sign here. N minus means very low density N material. Very low density N material. This N minus region, N minus layer, can be considered, in many situations, can be considered as similar to intrinsic semiconductor. And therefore, you got the ability to deal with higher reverse voltage. And we can imagine if you want to deal with even higher reverse voltage, what you need to do is just to increase the thickness. Increase the thickness of this N minus region, N minus layer. And that way you can increase your ability to deal with higher voltage. Now, there will be a problem. Okay? Of course, increase the thickness of the intrinsic layer can give us larger ability to handle the higher reverse voltage. But what happens when we need this diode to be conducting current? When you apply positive voltage, when you apply forward direction voltage to this diode, we want this diode to be able to conduct larger current. Okay? Of course, it has larger size, it has vertical oriented structure, but now you have a intrinsic semiconductor layer between P and N. And we know this intrinsic semiconductor layer is very similar to insulator, right? Then in the forward direction, how can we have this intrinsic layer to allow very high current flow through? And that's the problem. So on one side, increase the thickness of intrinsic layer, you get higher ability to handle large voltage, but how do we handle the current when you need the diode to be conducting? The key is conductivity modulation. Conductivity modulation. This is a very special concept with power semiconductor device, especially with minority carrier device. Okay, this conductivity modulation is actually describing the phenomenon like this. You see, when you apply positive voltage to the P side, negative voltage to N side, you establish the outside electric field, which is pointing from upper side to lower side in that direction. And therefore, there will be a lot of free electrons in the N region be pushed into N minus region. Okay? Similarly, there will be a lot of holes in the P plus region. P plus, N plus, that plus side here. This means the density of carriers. Okay. Plus means you have very high density. Minus means you have very low density carriers. So when you apply positive voltage across this diode, this P region will have a lot of holes be pushed into this N minus region, this intrinsic region. This pointer is not working so well. And there's also a lot of free electrons be pushed into the N minus region. And therefore, you can imagine the density of free electrons and holes in the intrinsic region will become larger because you injected a lot of free electrons and holes into this N minus region or intrinsic region. And therefore, as your electrons density and holes density become increased, your conductivity becomes larger. Therefore, you can allow larger current flow through. Originally, this is the intrinsic N minus region, this is the intrinsic. But now, because you injected a lot of holes in here, a lot of electrons in here, this no longer is intrinsic. This is now having quite large conductivity. So you have current flow through. As the current flows through, you are injecting more free electrons and more holes into this region, and therefore your conductivity becomes even larger. This is called conductivity modulation. In the forward direction, because of the free carriers injection into the intrinsic region, the conductivity of intrinsic material becomes higher. And therefore, you allow larger current flow through. It is no longer similar to insulator. Okay? Those are the features, okay, that make power diode so different. That make power diode has the ability to handle higher voltage and an ability to allow larger current flow through. this is very important. All these features almost always exist for all the power semiconductor devices, not just for power diode. Okay. For many other power semiconductor devices, they all have these similar structures. They have larger size. Okay. They have vertical oriented structure. They usually have a N- region to deal with large voltage. Okay. The fourth one, some of the devices they have. If they are a minority carrier device, then they have conductivity modulation. Okay? If they're not, then they don't have this. They don't have conductivity modulation. Okay? There's an illustration in the following lecture notes showing when you are forward biased, when you apply forward direction voltage, it's also called forward bias. Okay, when you are forward biased, you are injecting, because of the outside voltage or outside electric field, you are injecting holes from P region to this intrinsic region. You are injecting free electrons from N region into this intrinsic region. And therefore, the density, carrier density in the intrinsic region is dramatically increased. Therefore, you have the ability to allow current flow. Your conductivity becomes larger. That's the illustration. When it is reverse biased, when it is reverse biased, you can imagine the originally inside intrinsic region electrons and holes will all removed. Electrons will be removed from intrinsic back to N region. Holes will be removed back to the P region. Okay? Therefore, there will be no carriers or very small carriers in the intrinsic region. Therefore, in the reverse biased situation, this intrinsic region will get the ability to handle high voltage. Because now, no carriers or very small density of carriers, therefore it is similar to the insulator in reverse bias direction. Okay? Of course, there is a limit. There is always a limit. The ability to handle high voltage, there's always a limit. When this voltage is large enough, there will be avalanche breakdown. We have a special name for that in Chinese. Breakdown. When this voltage is too high. Okay? Usually this breakdown is called avalanche breakdown. When avalanche breakdown happens, if you have the ability to limit the current flowing through, you still can keep the diode safe. Although the voltage is very high, if you can still, through the outside circuit, limit the current very small, then this is still safe. But if you cannot keep this current small, then this current will become dramatically large. And we have very high voltage, very large current, you make very high power loss, energy loss on the diode, therefore you generate very large amount of heat, and you gradually destroy the diode. That's when you destroy because of the heat. Then it's called thermal breakdown. Okay. All right. In the structure, there's another issue we have to mention in the structure of power diode. That's junction capacitor. Junction capacitor is another thing we have to mention. Why there's junction capacitor? Because in the space charge region, in the depletion region, you have on one side positive charge, on the other side negative charge. That's by nature, that is a capacitor. Okay, so you always have certain capacitance. Capacitance. Capacitor means the component. Capacitor and capacitance means the effect that has the characteristics of capacitor. It's just similar to when we see resistor and the resistance. That's the same. Okay, there is. I will not get into details. There is two different courses of junction capacitors. There is a potential barrier capacitor. And there's also diffusion capacitor. Different causes of capacitor. You do not need to get into details of that. And the reason we want to mention this is that when you have a capacitor, that usually affects your switching characteristics. Okay. A capacitor, of course, will affect your switching characteristics. That means when the diode is changing from conducting to blocking, forward direction changing to reverse direction, you always need time. You need some time to change to a steady state. Okay? Because of this capacitor. This capacitor needs to be charged and discharged. Okay? So you need some time. Now the characteristic, this is very similar to information electronic diode. This is a static characteristic. When the horizontal axis is voltage applied to across diode. The vertical axis is current. Okay. When this forward voltage is large enough, then the width of space charge region will be reduced to a certain limit. Therefore, you allow very quick increase of current. The current to flow through this diode. Okay. When you apply negative voltage, usually there's no current or very small leakage current. Very small leakage current. very small leakage current, until when this reverse voltage has reached a certain limit, reached your breakdown voltage. Okay, then the diode will be broken down. Okay, that's very similar. This is the IV characteristics of power diode, similar to information electronic diode. But this is different. You never see this before. Switching. In the analog electronics course you learned before, you never talk about this. But here we have to talk about this. Switching means when you turn on or turn off, when the diode is changing from forward direction to reverse direction, or changing from reverse direction to forward direction, how the diode is performing. That's called switching characteristics or dynamic characteristics. This is complicated. You would imagine, before this, you would imagine when the diode is turned off, you would imagine if this is the current, waveform, and this is the voltage waveform, and then you would imagine when this diode is changing from forward bias to reverse bias, you would imagine the current will be changing to, let's see, 0. Current changing to 0. And the voltage, originally, this is a forward. The voltage across the diode will be nearly 0 because this is conducting. And then when it is changing to reverse bias, this will be changing to reverse voltage. All the reverse voltage will be applied to the diode. Okay? That's what we imagine. But actually this is not. The actual waveform is much more complicated. Much more complicated. Okay? The current, when you apply reverse voltage to a diode, when the diode is conducting, it will suddenly, let's see, from here, the outside voltage this is outside voltage. Let's see, changing from positive to negative. Suddenly changing from positive to negative. Of course, the current will be decreasing. You see, current decreasing, IF. We use this subscript. Current will decrease to 0. But it will not stay at 0. Because when the current flowing through a diode becomes 0, at this time, the diode has not recovered the ability to block voltage yet. There is still a lot of carriers inside the diode. There's carriers in the N region, carriers in the P region, carriers in the intrinsic region. So there's still a carrier. Therefore, when the current decreases to 0, those carriers are still there. Therefore, you still have the ability to allow current flow. So current still will be flowing, but in the reverse direction because the outside voltage has reversed. You have outside reverse voltage, therefore, because of those carriers are still there, so the current will still be flowing, but in reverse direction. Okay? Until when this reverse direction current flow, you gradually remove, because of the reverse current. Let me see if I need to change back to this. Okay, here. This is the original current flow. When you apply forward voltage, and therefore you have a lot of carriers inside the intrinsic region, so there will be current flowing. Electrons will be moving from this side continuously into the intrinsic region, continuously move on and to the P side, and then through the outside circuit moving back. That's free electrons. Holes will be moving from P side into the intrinsic region, and then into this region, and come back to the P region through outside circuit. That's the moving direction when the diode is forward biased. When it's suddenly changed to reverse biased, this current will be decreasing and finally decrease to 0, but there will be still carriers inside this region. And because the voltage is now reversed, remember, you still have carriers inside this region, but the voltage is now reversed. That means the electrons in this region will be moving in this direction, pushed back. The holes in this region will also be pushed back to P region. Okay, that's the reverse current. And therefore, the density of the carriers in this region will be gradually getting smaller. And therefore, gradually recover the ability to block reverse voltage. Okay? So, in the end, after a certain time, the carriers inside intrinsic region will be removed, and therefore now this region recover the ability to block high voltage. And therefore suddenly the conductivity at here, the conductivity of the intrinsic region becomes very small, no longer be able to conduct current. And therefore the current will be dropped back to 0. Okay? So the actual process when the diode is changing from conducting from forward direction to reverse direction is like this. This bold line here, that's the current. Decrease to 0 and then increase in the reverse direction. And then when the intrinsic region recovers the ability to block voltage, this current decreases back to 0. This process is called reverse recovery process. Starting from this point, when the current decreases to 0, until this current drops back in the reverse direction, drops back to close to 0 again. This is called reverse recovery process. So this is very complicated. This is not like what we imagined before. Okay? So this process, starting from here to here, this is called reverse recovery time. The time starting from here to for the current come back to 0 again, this is called reverse recovery time. Okay? And this reverse peak current is called reverse recovery peak current. Reverse recovery peak current. Okay? And only when the diode recover the ability to block reverse voltage, the actual voltage across the diode will be increased to equal to the outside voltage. Okay? And similarly, there is another concept, reverse recovery charge. Reverse recovery charge. Reverse recovery charge means how much charge you need to remove from the intrinsic region so that the intrinsic region will recover the ability to block high voltage. Okay? Similarly, when you turn on, when you are changing the diode from off state to on state, or from reverse bias to forward bias, there will also be a transient process. There will also be a process. But usually this process, this time, changing from initial time instant when you change the outside voltage from reverse to positive, starting from this point, until the current flowing through the diode becomes a certain value. This time is very short. Actually, this forward recovery time is much shorter than reverse recovery. So usually when you use diode, you never care about this. You seldom care about forward recovery. Usually you care about reverse recovery because reverse recovery time is much longer than forward recovery. Okay, there are some specifications for diode, for power diode. I will not get into details, specification. You read through the lecture notes and the textbook after the class. Okay, there is, when you talk about average rectified forward current, average rectified forward current. Okay, there is a definition in the textbook. I will not get into details. These are used to, this specification is used as the rated current or nominal current. Of power diode. We use that to label the nominal current of a diode, power diode. And then you have forward voltage. Okay. That's the voltage when you apply certain current. When the diode is forward biased and you allow certain value of current flow through the diode, at that time, how much is the voltage across the diode? That's called forward voltage. And then you have peak repetitive reverse voltage. Peak repetitive reverse voltage. That's used as nominal voltage or rated voltage. For power diode. That means when you apply a reverse voltage on the diode repeatedly, what is the maximum peak voltage a power diode can sustain? Or what is the maximum peak voltage a power diode can block? That voltage is used as the rated voltage or nominal voltage for power diode. Okay. Maximum junction temperature. Junction temperature. That means if the diode is operating correctly, what is the maximum temperature this p-n junction can sustain? Okay, that means you always want to keep the temperature, the actual temperature of this p-n junction below that level. If you are reaching that level, you are reaching the boundary of destruction. Okay, maximum junction temperature. Reverse recovery time, we have mentioned that. Okay, reverse recovery time, we have mentioned this specification. Those are the specification we usually use to describe a power diode capability. Okay, and there are several types of power diodes. You have general purpose diode. Another name is rectifier diode. General purpose diode or general purpose power diode. Okay, and then you have fast recovery diode. In many cases, we need power diode that has much faster reverse recovery process. Okay, then we build some fast recovery diode. Sorry. Fast recovery diode. That means the reverse recovery time is much shorter than standard power diode. Okay, it could be a reverse recovery time is usually less than 1 microsecond. Microsecond. And many are even less than 100 nanosecond. Nano. Did I mention this? Micro is actually multiplied by 10 to the minus 6 power. Nano, this is 10 to multiplied by 10 to the minus 9 power. So even less than 100 nanosecond. That's called ultra-fast recovery diode. Then there's another type of diode which is totally different. The structure is totally different from PRN diode. This diode is called Schottky diode. Another type, Schottky. This is very different from the ordinary PIN diode. This is no longer based on p-n junction. Okay? The structure and operation principle is totally different from p-n junction diode. And therefore, we will not get into details of physics of operation of this type of diode. What we need to know is that this type of diode has no reverse recovery process, because there's no p-n junction there. Okay? Essentially, no reverse recovery charge. Okay? So that's good. That means when you turn this diode from forward bias to reverse bias, this changing process is very fast, much faster, even much faster than fast recovery diode. So that's good side. So we need a lot of Schottky diode in the future when you need to turn on and turn off diode very, very fast. But the bad thing is, this is very restricted to very low voltage, very low reverse voltage. The ability to handle voltage is not so good. Usually it is less than 200 volts. We don't have a Schottky diode that can handle voltage higher than that. So that's the bad thing. Okay, so when you need to handle reverse voltage higher than this level, you have to go back to PIN diode. There's a picture showing, this table showing some of the examples, some of the commercially available power diodes. There are many manufacturers, many companies, they are building different power diodes. Okay. I will not get into details. There are international companies, there are also domestic companies building the power diodes. Okay? This page shows the history, a little bit about history. The power diode has been in use since 1950s. This was invented, power diode was invented before thyristor. Remember, in the first class, we mentioned the invention of thyristor was a major breakthrough in the history of power electronics. But before thyristor, a diode was invented. They're still in use, okay? Because although diode is not a controllable device, it is uncontrollable device, because we cannot, a diode can not be controlled through information electronics. Okay? When you apply forward voltage, it is conducting. When you apply reverse voltage, it is blocking. So it is totally depending on the power circuit, totally depending on the external power circuit. There's no controllability from control circuit. But still in use, the reason is, in the future you will know, in the following chapters when we talk about power converters, all different power converters, you will know you always need diodes. Even you have thyristors, even when you have fully controllable devices in the circuit, you always need diode to work together with all those controllable devices. So that's why we need to talk about diode in detail. Okay? So you always need those. Those are necessary. Power diodes are always necessary components in almost every power converter, even when you have fully controllable devices there. Okay? And in many cases, fast recovery diode or Schottky diodes have to be used instead of general purpose diodes because in many cases we need this diode to be turned on, turned off much faster. Okay? And therefore, you need fast recovery diodes or even Schottky diodes. Okay, that's all about power diode. Do you have any questions so far? So you already have a feeling how are we going to talk about the following devices. We spend more time here because a diode is the simplest power devices. And there's also a lot of features in the power diodes that is actually also true for all the following devices. And we have a lot of basics here. So that's why I want to spend more time here. Okay. So you have a feeling, and then in the future you will know when you learn a new device, there are several things you have to pay attention to. Okay. Of course, you have to pay attention to the what is the structure, the inner structure. Okay. And what are the names of their terminals? A different device has different names of terminals. Okay. For diode, we have anode, cathode. For other devices, you have different names. Okay. Okay. What is the symbol? Okay. A diode is simple. The symbol of diode is the same as what you learned before. But for other devices, the symbol will be different. Okay? So those are the things you want to know. And what is the inner structure and operation principle of each device. Okay? And when you talk about this part, this is the most difficult part. When you talk about the inner structure and operation principle, this is the most difficult part. But when you learn this part, what you need to do is just to pay attention to the key points. What makes this device different from other devices? Okay? Always remember this question. What makes this device different from information electronic device? And what makes this device different from other power devices? These are the key points when you understand the inner structure and the physics. Okay? Any questions? We can have a very quick question. Probably you don't want to ask question. You're already want to rush to the dining hall. All right. That's all for today. I'll see you on Thursday.